Hello everyone and welcome back to lecture 5 of machine learning techniques. Today we are going to look into PCA and LDA, both of which are dimension reduction techniques. So why do we want to reduce dimensions? Why isn't more data better? The thing is, as you add more and more features, data becomes very sparse, which means a lot of zeros, and the data points are going to be far from each other and far from everywhere. For example, we can look at this analogy, a finding a friend analogy, where if you have two features, it's a less dimension. You can find someone of your city of a similar age, which means your dimension is age. Now, if you look at 10 features, you can add the music taste, the hobbies, the favorite food. So now you have more correlation. But then if you add 1,000 features, you don't match with almost anyone because you have to match with them on all 1,000. So more data isn't always better. So problems of this are obviously overfitting and slower training because you have huge amount of data. So how do we make data simpler? We do this through feature selection and feature extraction. So feature selection basically is if we have multiple features, we only pick few features. And feature extraction is you can club two or more features together to make one singular feature, which anyway gives the same amount of information to a machine learning model as those two features individually. So today we are going to look at feature extraction using PCA and LDA. What is PCA? PCA is a principal component analysis. It is basically unsupervised vision. So it finds the directions of the data in which the variance is basically the spread of data. So we want to find the most spread out form of data in a particular dimension. So assume you're a photographer and you want to take a photo of a pencil. If you put the pencil standing up and look at it from the side, it's going to be very long. But if you look at it from the top angle, it's just going to be a small circle. So this way you can reduce the dimensions of the data. So let us assume we have a scatter plot of different points. We have a 2D scatter plot here. The points are as shown. So we are going to find PC1 or the principal component 1, which is the direction of maximum variance. This is usually along the axis of the ellipse. And next we also find PC2, which is always orthogonal to the PC1, which means it is 90 degrees to the PC1. So now we have two dimensions. Let's say we want only the PC1. We want to make everything into one dimension. Then just take PC1. So the points along PC1 or the line PC1 becomes the 1D dimension. This way you have reduced the dimension. This is an interesting visual on how PCA works. As you can see, you have a bunch of data points here. They have no labels, which means it is unsupervised training, and you want to find the principal component or PC1, which means you want to maximize the spread of data, or in professional terms, you want to maximize the variance of data in a particular direction. And this is how it is being done. So how does PCA work? Let's think of it mathematically. It works on something because of eigenvectors, because we want to find the directions of the principal component PC1 or PC2, which maximize variance. How do we do this? The first step is always, to have a mean of 0 and a standard deviation of 1. We want to center the data along the mean. Then you find the covariance matrix to find how each and every feature collaborate with each other and how they impact the other feature together. And then you find the eigenvectors and the eigenvalues for that particular covariance matrix. And then when you find the eigenvectors, they are your directions, and the eigenvalues tell you the amount of variance captured by each eigenvector. So now you're going to have, let's say you have a 5-dimensional space, you're going to have 5 different eigenvectors. If you take the top 3 eigenvectors, then your dimension becomes into a 3D plane. If you take the top 2 eigenvectors, it becomes into a 2D plane, and so on. So this is how you reduce the dimensions in a PCA. This is a very simple visual for you to understand. You have a lot of data which is correlated, then you center the points, which means you have mean of 0 and standard deviation of 1. You compute the covariance matrix. Since it's a 2D data, you have a 2 cross 2 covariance matrix. Then you find the eigenvectors and the eigenvalues for that particular matrix. And accordingly, you select the number of dimensions you want. Here we will select only one dimension, which means we select the highest eigenvector or the eigenvalue. And alongside that, we plot the data points to find this to be the final one-dimensional version of this data. So where do we use PCA? Where is this dimension reduction, especially in a unsupervised way, being used? Image compression is very simple, where you can capture most important parts of an image with few components, or if you want to visualize data, as we have seen so far, into a 2D or a 1D plot from a 3D or a higher dimension plot. And obviously noise reduction, because here we are plotting everything with mean 0 and variance 1. The outliers have very low variance, which means they can easily be filtered out. Now, we have looked into unsupervised way of dimension reduction. What if we have labels? What if we want to do a supervised way? For that, we have linear discriminant analysis, which means we find the best separation between classes, or rather, we try to maximize the variance between two classes, and you want to minimize the mean within the class. You want to minimize the variance within the class. Sorry. So here, what is variance and what is separation? You have labeled data. As you have seen, PCA is just going to put all the points together as one and try to maximize the variance between data. But LDA tries to maximize the distance between the different classes, because PCA is unsupervised. So LDA maximizes the separation between categories. PCA maximizes the spread of the data. This is a simple way of how LDA works, where you have spread of data and then you try to make it a bit more ordered in order to maximize the variance between the classes. So how does LDA work? Basically, we want to maximize a ratio. What is this ratio? It is a ratio of between class variance to within class variance. We want to maximize the difference of data between two different classes, but at the same time, we want to keep the variance within a class very minimum or very close. This way, your clusters are, or your labels are very close to each other within a particular class, but amongst two different classes, they are spread out very wide. So how is this done? This is done through an algorithm by which LDA finds the new axis, which is called a linear discriminant, that makes this ratio as large as possible. What are the real world applications of LDA? Where we have labels. Medical diagnosis is a very common place where we use LDA, because we have to find a combination of medical measurements that best diagnoses between healthy and diseased patient groups. We have classes. Or customer satisfaction, where you want to separate the high value customers from the low value or likely to churn customers, or even facial recognition, because everyone's face has a particular label associated with it, and accordingly you want to reduce the dimension and want to find out in which way or how much variance varies from one person's face to another person's face. So, short summary, PCA is unsupervised, LDA is supervised, which means PCA uses labels, does not use labels, LDA uses labels. PCA maximizes the variance of the entire data set. LDA maximizes the separation between classes and brings in the variance within the class. And the goal of PCA is to describe the data structure. LDA is to build a discriminative model. PCA is best for visualization, compression, or finding hidden patterns, while LDA is classification problem with many features. Thank you and see you all in the next